Okay, so your practice problems. Number 7 says the Earth is revolving around the Sun in a nearly circular orbit. Okay, so this is the Sun, this is the Earth. The average distance from the Sun is about 1.5 times 10 to the 8th kilometers. So that's our R. 1.5 times 10 to the 8th kilometers, which is really 10 to the 11th meters. Okay, and then it says find the orbital speed. So we know that v equals 2 pi r over t. So 2 pi times 1.5 times 10 to the 11th meters, and t, the period, the time it takes to go around, I actually put in brackets for you in case. So it's 365.25 years, and I put it there because lots of people leave off the 2.5. The 2.5 is, that's why we have a leap year every 4 years, because you pick up a quarter each year. But you have to change it into seconds, so times 24 hours. That's days. Sorry, 24 hours per day times 360 seconds per hour. And when you do this, you should get a speed of 29,865.32 meters per second. Okay, that's part A. Part B says find the magnitude of the centripetal acceleration. So you're looking for AC, and we know AC equals v squared over r. So that 29,865.32 meters per second squared over 1.5 times 10 to the 11th meters. Pardon me. And you get an AC of 5.95 times 10 to the negative 3 meters per second squared. Part B. And part C says, what is the size of the centripetal force on the Earth? So we know that F equals ma. And so the centripetal force, which is an F net, should equal the mass of the Earth times the centripetal acceleration. So the mass of the Earth, 5.98 times 10 to the 24th kilograms, times the A that you just found, 5.95 times 10 to the negative 3 meters per second squared. Now you could have also done mv squared over r. It's just that we already did the v squared over r, so just to save a little bit of time. And when you do this, you should get 3.58. But that's really a 6. 3.56 times 10 to the 22 newtons. That's a fair bit of force. Okay, so that's your FC. All right, that was number 7. Number 8 says a merry-go-round makes 24 revolutions in 3 minutes. So remember, period is equal to the total time divided by the number of things that are happening. So in this case, the number of revolutions. So it says it makes 24 revolutions in 3 minutes. So 3 minutes times 60 seconds per minute divided by 24 is going to give us our period. And when you do this, on the top, 180 divided by 24 should be 7.5 seconds. Okay, so that's our period. So we can now use that to find the speed of a person standing 4 meters from the center axis. So for part A, v equals 2 pi r over t. So 2 pi, and it was 4 meters over 7.5 seconds. And you get a speed of 3.35 meters per second. In part B, you're standing further out. You're standing at 6 meters out. So it's still 2 pi r over t. 2 pi times 6 meters over 7.5 seconds. and that is the speed of 5.03 meters per second. So the people on the outer circle, the outer horses of the merry-go-round, are actually going faster than the people on the inside, which makes the outside more scary. Merry-go-rounds can be scary. All right, number 9 says a stock car travels around a curve that has a radius of 50 meters, so R is 50 meters. What angle must the curve be banked at if the car wants to go around at 100 kilometers per hour? So V is 100 kilometers per hour, and 100 kilometers per hour is 27.7 repeating meters per second. So it's a banked curve. All right, here's my car. And we're assuming no friction because it says absolutely nothing about friction. So this is Fny, and up here is Fnx. And so in the y direction, oh, this is Fg, who didn't label it, will be equal to May, which will be 0. There'll be Fny minus Fg equals 0. So Fn and the thetas are the same, so the y is cosine, will equal mg. So Fn will equal mg over cos theta. Didn't give us the mass of the stock car, so can't find anything else here. So move to sum of the forces in the x direction. And in the x direction, it'll be mv squared over r. It's centripetal. And the only force in the x direction is Fnx. So Fnx is equal to mv squared over r. Fnx is really Fn sine theta equal to mv squared over r. Where the Fn is, sub in your mg cos theta, or mg over cos theta. So you'll have mg sine theta over cos theta equals mv squared over r. The m's cancel, sine over cos become tan. So you have tan theta, take the g down, equals v squared over g times r. Tan theta equals 27.7 repeating, and you're squaring that over 9.81 meters per second squared, and the radius was 50 meters. Take the inverse tan of both sides, and you should get 57.556. It's probably 5 repeating degrees. Now that is a huge angle. You would never see that angle on a regular road, but for stock cars, it would make sense. But most of our angles on roads are going to be like 20 something. Okay, they'll never be 57 because that's way too steep. Although you would see angles like that if you've ever done, ever watched the biking in the Olympics. You know, when they go around in the circle. Like, they say those tracks are so steep, are so banked, that you wouldn't be able to stand on them if you were trying to, like, just walk. And that's why the bikers, if they lose speed, they'll fall down to the bottom of the bank, the curve. All right, number 10. A curve with a radius of 70 meters is perfectly banked for a car traveling 60 kilometers per hour. So when you see the perfectly banked, it means the angle was figured out for this speed, and then without assuming no friction. What must be the coefficient of friction for it to travel at 90 kilometers per hour? So once we get the angle, then we need to find the mu for 90. And 90 kilometers per hour is 25 meters per second, and 60 kilometers per hour is, I can't do it in my head, 90 I could, is 16.6 repeating meters per second. Okay, so the first step is to do what we just did in the last question and find our theta. So I'll go through the steps again just because you haven't seen them a lot. So this will be Fg going down, this will be Fn going up, Fny, Fnx, and we assume no friction to start with. So the sum of the forces in the y will equal 0, going to run at a time.
So Fny minus Fg equals 0.